If you do oversize your pump, you can run across many different issues that can cause many problems in the long run. Number one, if you're pumping off or you're running into cavitation. Say if you're pumping milk, if it's coming out and it has like a milky substance to it, if you're pumping off, either valve it back or, which I'll talk about in pretty soon, is VFDs. Slow it down, pull it back a little bit, because one thing that you're doing, you're increasing the possibility of introducing sand into your well because you're putting more stress on the well to introduce sand or bring something in or to even pump off. And when you do that, you put stress not only on your motor, but on your pump and your well as a whole. And also, one thing I want to talk to you about is VFDs, as far as what VFDs can do. It's a new technology. It's a fast-moving technology in the irrigation world. And one thing you can look at it is the cruise control for your pump. And that's exactly what it is. More or less, you set it to what your needs are, and you start, more or less, you drive off. And what it does, it either tells it to speed up, slow down, many different angles, what you can do with this. And one of the earliest forms of the VFD is a hand pump. However fast you want to churn it, that's whatever kind of water you want out, you have to put into it, depending what your needs are. But that is one of the earliest versions of the VFD. But one of the main reasons why you want to look at a VFD, energy savings. Why is it energy savings? Because it meets demand of what you actually want out of it. It's not running full speed. So if you have a system that requires 50 pounds of pressure, however, your system only needs 40, it'll slow down to whatever is needed versus running full speed across line start. There's, as I mentioned earlier, you have your constant pressure, constant flow, depending how you want to set it up. You do have savings. And also it prevents from water hammer. More or less water hammer, when you first kick it on, your pipe just slams because what it's doing is just bringing water so fast down that line. And that what it can do, you can start breaking pipelines, you can start doing many different things. When VFDs are a good choice, I'm not saying you can buy a VFD and you're guaranteed energy savings. It has to be a particular choice. One thing that you can look at as a whole, you have to have variable variety within your system. Whether if you're in a drip system or irrigation system where if you're in multiple zones and one zone's larger than the other, but yet you want to keep a constant pressure in there, and one zone only requires they all require 50 pounds of pressure. However, one only requires 20 gallons a minute with that 20 pounds of pressure or 50 pounds of pressure. So one thing that you can look at is it only keeps what your demand is, and one thing to look at. Also, systems that run all over the curve, you need something consistent, and what that drive does is keep it within the line of what your needs are within the system. And also, for systems that are oversized, as I mentioned, I've probably been in this industry probably 15, 16 years. I see probably 50% of the jobs sized are oversized, and that's when they can put in a VFD, and not only the energy savings, then pulling that motor back, it pretty much pays for the system within 1 to 2 years. One thing to also look at is life cycle cost, and what life cycle cost is from the initial purchase to the installation, the operation, maintenance, long-term goals, and electricity. One thing to look at as a picture of make it pay for itself as far as the lifetime cost, because many things to look at within this lifetime cost cycle. This is a proven fact. Over 70% of the U.S. energy used today is run on motors. And within that, the 70% of that is run on pumps, compressors, and so forth. So when you do that, 20% of the United States energy is ran on pumps. That is a lot of energy to be used. And when systems are oversized, that's something to look at as a whole. So you look at this as a whole, and the energy and the maintenance of the cost of that is almost 10 times of the initial cost of the pump. Because you look at all your energy costs and everything in the life of the pump, it almost runs 10 times the cost of the original cost of the pump. So that's one thing to look at as a whole. And then also, as I mentioned earlier, 70 to 90% of the pumps are oversized. So that's one thing you can put a VFD on to slow it down to go to the initial cost to look at. This is just another quick slide just showing what your costs are in, say, a system, whether it be, I call them a pump system versus a pump plant. It's just a whole system, what you're looking at, whether it be the irrigation system, the pump, and everything as a whole, what your initial costs are in the overall system. And also, we're not claiming that this is environmental or anything else, but we do know for a fact for every kilowatt hour produced, it produces 600 grams of CO2 to release in the environment. We're not saying it's anti-environmental or anything else, but it does have something, it does put that in the environment as well. One thing to look at as far as your lifetime cycle cost as well, energy savings, as I mentioned earlier, can pay for itself within 1 to 2 years. With also your reduced speed and over the time, it can reduce the wear and tear on these pumps because you're not going full speed, so you're reducing the wear on your rotating parts. And also it can also prevent some of the untimed scheduled pullings or settings because it is a soft start, which is a very good thing, which I'll talk about here in a minute. With the electronic pump controller, many different things you can set it on. If you want a constant pressure, constant flow, constant temperature, I'd say probably 99% applications for irrigation would be constant pressure, depending on what your needs are. And when it shows this, as far as when you're sizing one up, you pressure it up, you have a transducer, which is the brains for this whole VFD. What it does, it goes to what your demands are. Say if you set it at a constant 50 pounds, and it keeps it constant. So when it speeds it up and slows it down, typically because your ramps and your RPMs, what it does, wherever your point is on the curve, it follows your efficiency. So your efficiency follows that pump. So you keep your efficiency of the pump within the system. And you can control the unit depending on what the speed of what your needs are. And it signals the motor, either speeds up, slows down. And this is more or less what it does. This is your standard speed as far as your voltage, what it does over time. And then when you put it on a VFD, when you need to speed it up or slow it down, it more or less stretches it out. So you're not using your cost of your inrush current and so forth of your amp draw to what creates more or less the cost on your bill. And what I talked about earlier as far as starting sequence, what that does on a VFD, it incorporates a soft start. And what that soft start does, typically on an everyday irrigation well as it is today, they have once it starts, there's an inrush current, an amp draw from 2 to 10 times the amount that's standard. And what that does, that inrush current that comes into that motor, that's what creates your torque and everything else. When you put it onto a VFD, you can still get that torque, however, it does not have that full inrush of current. And when you have that full inrush of current, what that does is get the motor hot. When you get the motor warm, all it does is start degrading or breaking down insulation in your motor. When you break down insulation in the motor, you shorten the life of the motor. So one thing that also does, it creates the longer life on the motor as well. Infinity laws, I'll touch on these real quick. What the infinity laws are, what a VFD can do, it can go over your head if you don't watch it. And what it does, whatever the flow does, or whatever the speed does, the flow does. Whatever the speed does, the head does, but squared. Then also power, it cubes it. For example, if you decrease the speed of a pump, and speed is typically referenced as far as the VFDs in hertz, from 60 hertz to 48 hertz in this particular example. If you decrease it by 20%, what it does, it more or less, you have 80% of your flow, 64% of your head, and 51% of your power. So it cuts that much power out of it, and something to look at as a whole, one thing that you do, what a VFD can do in this system. As far as an example for a system, what a pump can do in a VFD system, you have one main pump supplying many different zones at particular times. And as I mentioned earlier, one zone might be larger than the other, and what the pump will do, either speed up or slow down. As you can see, these this isn't a perfect drawing or anything, but you have multiple triangles that are different sizes, so therefore you have different zones and different sizes, so it'll speed up to what your needs are within the system. I know this is a busy slide, but it's similar to the other one, but it's tied to a VFD. What kind of savings would you provide using a VFD versus a standard system? And what we have here, this particular item, we're using a 4500